Complex analysis is a profoundly beautiful and powerful branch of mathematics. This video explores how it extends the familiar concepts of real calculus into the complex plane, beginning with the foundations of the plane itself and progressing to the requirements of holomorphic functions. We begin with the complex plane, or Argand diagram. Here, complex numbers are represented geometrically, defined in Cartesian coordinates as z equals x plus iy. We also look at their polar representation and Euler's identity, which elegantly connects the most important mathematical constants. Next, we examine complex functions. Unlike real functions, these map two-dimensional surfaces to other two-dimensional surfaces. This means we are mapping entirely separate planes, rather than simply plotting a curve on a graph, transforming input points in the z-plane to output points in the w-plane. Holomorphic functions introduce a more restrictive type of differentiability. For a function to be analytic or holomorphic, it must possess a complex derivative at every point in an open set. This is governed by the Cauchy-Riemann conditions, which establish a rigid geometric relationship between the components. Contour integration extends real-line integrals to paths in the complex plane. In a simply connected domain, the integral depends only on the endpoints. However, if a closed contour encloses a singularity, the integral may not be zero, as described by Cauchy's integral theorem. When functions blow up at certain points, the residue theorem becomes an essential tool. It provides a highly efficient method for evaluating closed contour integrals around these isolated singularities, offering an elegant algebraic shortcut to solve what would otherwise be difficult real-valued integrals. Finally, we look at real-world applications. From fluid dynamics and electrostatics to quantum mechanics and aeronautical engineering, complex analysis remains an indispensable foundation. Conformal mappings, which preserve angles and shapes, are critical tools used across these advanced engineering and physics fields.